Hey, what's up everyone? Jason Turley here, back with another video. And we've been kind of dabbling in firmware analysis lately. In the last video, we checked out like very gentle introduction to it. And I wanted to keep the ball rolling and I want to continue on. And I found this great project online called the Damn Vulnerable Router Firmware. And this is from Black Owl, who's a security researcher and makes a lot of great content and work out in the community. And he has this GitHub page where you can download and install a vulnerable piece of firmware that is running MIPS assembly, 32-bit MIPS assembly. And it's just a great, and he even notes this here, it's just a great way to get practice with exploiting memory corruption vulnerabilities like use after free attacks or buffer overflow attacks and things that aren't your traditional x86 or x64 architecture. This firmware is running MIPS, which is very common in the IoT and embedded systems space. And he does link here to some getting started pages, but if we click here and open it in another tab, this page is not found. So this has been moved over here, or there's just a slight typo in it. So if you can see at the very top, it says version 0.1. That's incorrect. We want that just to be version 0.1. And I'll leave a link to the actual blog post that he links in the description below. This isn't mandatory reading, but it is written very well, and he does go over some tools that you'll need. So you will need some type of emulator, unless you're going to be using physical hardware that you have. You will need some way to actually emulate this firmware, this router, and the one we'll be using is QEMU, which is simple enough to install on Linux, Mac, and Windows. We'll also be using binwalk, and you can use the default one that will come installed in most Kali Linux distributions, or you can install it yourself. But there's also and I learned this recently, there's a updated binwalk. And if we go to the GitHub page here, we see the last commit was 5 days ago, and this is written completely in Rust, and it's very fast and it adds color to output. So that's what I'll be using. And then the last tool that he recommends building is build root. So this isn't necessary, and I will show a different way if you don't want to install build root. But what is that? If we click here and we open it, it's from UClibc, and you're probably familiar with the C standard library that most applications are built with. UClibc is for embedded Linux systems. So it's just smaller and it has a lot of the same functionality, but it's just a smaller binary. Because as I said in the other video, working with embedded devices or IoT devices like routers or smart cameras, size is very important. So if you can make your executables and your binaries more compact and smaller, and then that's just better because it's going to save a lot of CPU resources and storage space and whatnot. So if you want, you can go here, you can download this, and it will come with a tool suite of like GDB and object dump and other binaries like that for MIPS. If you just use the default ones in Linux on a MIPS binary, they might not work as expected because they're going to be expecting whatever CPU architecture that you're currently running, which is probably x64. And if we go back to his GitHub repo, he does have a folder for GDB, and this does contain a GDB version that can handle MIPS and Little Endian and Big Endian. So with all that talking out of the way, let's actually get started. So I'm going to click here on code, and I'm going to grab this GitHub link right here, and we're going to go on over to our terminal. And if I do an ls and I go into my firmware directory, if I do an ls, we see I already have this project installed, but I figured what's the fun in that? Let me actually do it from scratch with you guys in case anyone wants to see how you actually grab the GitHub link and extract the firmware with binwalk and how you kind of set up your environment and whatnot. So it is a little beefy, so it is taking a little bit for this to download. So if we do an ls, we see a couple of folders here as long with that readme from the GitHub repo. So the firmware is what we're going to be most interested in today, but there's also the source code for the vulnerable executables that we'll be attacking, the source code for the firmware, and then GDB for MIPS, because we will be needing that later on. So let's navigate into the firmware directory and see what's going on here. We only have two things. We have the actual firmware that we want to look at and extract, and then we have the license file. So let's run binwalk on this firmware. I'm doing it with no command line options, so it's just going to print out what it has found by looking at the magic file headers inside of this binary. And it's found one thing, a firmware image. So let's actually see if we can extract it with TAC E for extract. TAC M will make sure it's recursive. And let's run it. It spits out a lot to our screen, and we can see here squash fs root. So this is the actual file system that is being extracted. And we can scroll up and see what else it has gotten for us. We can see the version of Linux being used right here is 2.6.22, which is very old. We see a note here saying it's from 2016. We can fact check that to see how accurate that is. Nice. So let's actually do an ls. Let's navigate to the extractions directory, and we want to grab the file system. So first we need to find it. I think it's in partition 1. Yeah, there we go. So this is a lot of directories to navigate down. So I'm actually just going to move this. So copy it, and let's move it up a few directories. And we're going to do firmware and fs. Now let me navigate to that directory. And we see it has the file system actually here. And if we want, we can kind of poke around. We can see what binaries are installed on the system. Unsurprisingly, a lot of these utilities point to BusyBox, which is very common for routers. They're not going to have their own custom-made executables. They're just going to use BusyBox, which is one utility that has a bunch of additional functionality, kind of like a Swiss Army knife for Linux binaries and whatnot. We don't see a home directory or anything like that. We can look at Etsy and see if there's any init scripts or anything like that that we want to poke at. But what we're actually curious about here is going to be this pwnable directory, and that is going to store the different challenges for us, right? This is basically a CTF. If we want to look at the README, we can. And it says, congrats. If you're reading this, then you either connected to the router over UART, so like the physical router, but we don't have that. Or you extracted the binary with binwalk. That's exactly what we did. Anyways, these pwnables are for teaching you how to exploit other CPU architectures. And in this case, it's MIPS 32-bit with a little endian format. And then it tells us the three challenges, the three binaries that are located here. The first one is stack buffer overflow. This is your run-of-the-mill buffer overflow. This does not require shellcode to win. There is a function compiled into the binary that is impossible to reach normally. Your goal is to reach that function, which will display a congratulations message and execute bin sh. And then we see some more for heap overflow and then a use after free. But for today, the focus of this video, just to get our feet warmed up and everything like that, we're going to start with stack buffer overflow. So reading this, if you've done any type of CTF challenges in the binary exploitation category, there's a category of like return-oriented programming. So hijacking the normal flow of a program and having it go somewhere else. So in this case, we don't need to return to libc or execute our own shellcode. The way that message was written is saying that there's a pretty much like a win function or like a get shell function that we can change our program to return to, and it'll execute the congratulations message as long with the bin sh, which is just a interactive shell on that system. So that is awesome. So we want to run this program, right? But if we just do a / and try to execute it, we're going to get an error. It doesn't know how to run the file, or I guess more precisely, if we run the file command on this, we can see it's dynamically linked, meaning all of the functionality, the library code, the shared objects that it needs are not contained within the binary. They are expected to be somewhere on your file system. And the interpreter that is, oh my gosh, I can't talk. The interpreter that is using is here, the loader or the linker, uclibc.so. So this is not our native interpreter that I have here on my Ubuntu VM. If I do like file bin sh, come on, file bin bash, here we go. We can see this is the interpreter that we're expecting and that we have installed on our system. We do not have this one installed. So how can we actually run this MIPS dynamically linked executable? Well, we can use QEMU or QEMU, however you prefer to pronounce it. So I'm going to navigate up a few directories and we're going to run which QEMU MIPS endian little and static. That's where it's located. And we're just going to grab this and copy it here. So now we can do QEMU and we need to navigate to this pointable file, intro, stack before overflow. And it still doesn't like it. So is that, so if we do an ls, okay, so we can see that the loader and the linker that it wants is right here. It's still trying to use our default linker. So if I do this and we look at strace and we scroll up a little bit, we should see what it's trying to grab. Yep, right here, we can see a call to open at. So it's trying to grab this file from /lib. So if I do an ls on /lib ld star, we do not actually have that here. So what do we need to do? We need to tell QEMU not to use our /lib, but we need to tell it to use the one that's in this current directory. And we can do that with the change root command. So change your root file system to the current directory, and then run QEMU MIPS endian little static, and then we want that pointable file stack buffer overflow 01. Need to enter my password. And this time it worked. If we do an strace on this and we scroll up a little bit, we should see it try to grab that other linker. Okay, so if we rerun this, and this time we add TAC-E open at to only look for expressions for open at, we should be able to see it grab the correct linker. We still see a bunch of errors like -1, no such file found. But I guess it doesn't matter. I guess you can just take my word for it or play around with it a little bit further. But we know if we do run it, it does work. It does print out the usage information and it's saying, hey, you're missing an argument. And then they just print out the name of the author who created this. So let's see if I do an up arrow and I type something like please sub. You entered the first buffer overflow exercise. You entered please sub. Try again. Okay, so we know we want to somehow overflow this program and we want to jam in a bunch of random characters and whatnot. An easier way to do this is to use Python. So if I do something like $Python3 TAC-C to run this command, print A times, I don't know, 300. And then we need to close up these parentheses and these quotes. It will print A bunch of times. And now if I take this and I throw it at the end of here, this command, it'll throw in a bunch of A's and we get a segmentation fault. Awesome. So we were able to crash this binary, crash the program, but so we probably overwrote the return address or the program counter with our A's, but we don't know how many A's it will take. So in order to analyze it, something we can do, I guess we were given the source code for this, so we can just look at that. But let's actually see if we can analyze this binary anyway. And I like using GDB for that. So we will need to be a little crafty in our GDB session. So I'm going to hit up arrow and go back to this line that we ran. And I'm going to, right after the QEMU MIPS static, I'm going to do a tach G and then 1, 2, 3, 4. Tach G is telling QEMU to basically open up a listening socket on whatever port we give it. I'm just giving it 1, 2, 3, 4, just something easy to remember. And if I hit enter, we see the program kind of hangs. But if I open up a new terminal and I do a sudo, I don't think I even have netstat on the system. Which netstat? No, but I do have ss. So if I do a sudo ss pants, and then we kind of just grep for ports 1, 2, 3, 4. Need to enter my password. We can see that QEMU is listening on port 1, 2, 3, 4, which is awesome. And we want to now open up a GDB session. But if I just do regular GDB that is installed on my system, and I just say target remote localhost on port 1, 2, 3, 4, it kind of looks like it connects. But if I hit run or continue, nothing really happens. And the issue is we're using regular GDB. So file which GDB. This is our ELF 64-bit executable, and it's just not playing nicely and working with this binary that we actually want to analyze. So let's rerun this, and let's use a proper version of GDB that we can get either from this build root. So if I open up a new pane, I went ahead and installed build root and everything following along Black Owl's guide. So if we go to cd output host, and then where is it? I think it's bin. Yeah, cd into bin, and we do an ls. We can see all of these additional binaries that we get. We care about this one right here, MIPS, endian little, build root, Linux, UC libc, GDB. And we can also do things like run object dump or readelf or strings. And these are just a bunch of like tools that we have that will work with this MIPS binary. But if you just want GDB, which is perfectly fine for this, we can go to the GDB folder that's included in the GitHub. And we just keep navigating here, MIPS, little endian, and we just run GDB. It's going to print a bunch of crap, so we can just do tach q for quiet. And now we do target remote localhost 1, 2, 3, 4. We can see that we are correctly inside of our debugger. And if I hit C, we do see that we've continued the program and we've exit with a segmentation fault. If I do an info register, we can see the different registers that we've kind of overwritten here. So if this is your first time looking at a MIPS binary and you're used to x86 or x64 or ARM, the name of our registers are very different. So we have A0 through A3. So these registers are for the arguments being passed to a function. In x64, function arguments are passed at first into the registers, RDI, RSI, and RDX, and so on and so forth. And then they'll be put on the stack. In x86, function arguments are placed onto the stack. Well, in MIPS, they're placed into registers A0 through A3. The registers that start with a T are temporary registers. They are just like general purpose registers. They don't have any real special value. I believe V0 and V1 are like return addresses. SP points to the current stack pointer. RA contains the return address, and PC is where our program counter currently points to. So we've overwritten the program counter. So in x64, this would be RIP, the instruction pointer register. And there's some other registers here that we can look up if we're really curious. GP is the global pointer. It points to, I believe, like the BSS segment of memory for like global variables. We have the 0 register, which is just always 0. And there should be an FP somewhere. I don't see it right now, but the frame pointer register is also a thing. But what we're most concerned with is this program counter. And we want to figure out how many bytes it actually takes to overwrite it. If I clear my screen, okay, I guess I can't clear the screen. So if I examine, let's say 24 gigs as hex from our stack pointer, we can see our A's being written here. So I'm actually going to quit out of this. Well, I don't need to quit out of it. Hit C to continue again. All right, our program is no longer being run. And this time, instead of spamming 300 A's, we're actually going to get a little crafty. We're going to get clever, and we're going to generate a pattern. There are tools to do this through the browser. I'm just going to open up a web browser, and I'm going to navigate to this website. Pattern generate buffer overflow. And I'm interested in this first link right here from wiremask.eu. And I can give it a length of how many bytes that we want to fuzz with. So I'm going to say 300, and it outputs this special sequence of bytes. They're not random. They're always going to start with this, a capital A, lowercase a0, so on and so forth. It's a pattern. So we can figure out the magic of this in a second. So let's grab this, go back to our terminal, and we're just going to slam in this pattern that we got here. Now we're going to go back to GDB, and we are going to connect with target remote IP and port number. All right, it's waiting for our input. We're going to hit C to continue on, and we get a crash. If we do another examining of the stack, we can see it's not just A's, but it's that uniquely generated pattern now. So how can we use this information to our advantage? We can grab where we saw the crash happened. So grab this, come back to our browser, and now in the find offset field, we are going to slam in the value of that register that we got. And we can see here it returned 204. So it takes 204 bytes to get up to the program counter, and then anything we write after that will overflow the program counter. So let's test this out. Let's hit C to continue just to make sure the program exits. We're going to come back here. We're going to hit our up arrow, and we need to change this. So this is it was 300. We want to change that to 200. My window's getting all crappy. So we're going to grab 200 bytes of junk, slam that in there. And after those 200 bytes, we're going to add 4 bytes of a pattern that we know that we added. So I'm just going to do 1, 2, 3, 4 X's, and X should be 0x58. So if I rerun this program, I hit C to continue. Okay. That's not what we wanted. What's going on? Let's come back here. Instead of using this pattern, let's go back to our Python. And we're going to create 204. I think that's where I messed up. I did 200. It should be 204. And I'm going to do X because A and B are overused. Come up here. There we go. So OX58 is the value for X. So we know we successfully overwrote the program counter with whatever arbitrary value that we want. If I try to do an info functions, for whatever reason, it's saying there are no functions defined. It's really strange. I'm not really sure what's going on and why that doesn't work. But if we come back here, we can use a different tool instead. So I'm going to navigate back to this directory, firmware, file system, vulnerable intro. And let's actually use Robin2 with tac I. And we're just going to start looking and analyzing this binary. Because we know it's vulnerable to a buffer overflow. We know we control the program counter. And we want to change it to point to the get shell function or the win function. But we don't know where it's located. We don't know what it's called. We don't know what security mitigations are in place. So this is where you want to do some type of analysis of the file. And there's a million ways to do this. If you want, you can just open it up in Ghidra and it will do a good job of looking through and analyzing things. I'm trying to get better at using Radare 2 and its tool suite. So that's what I'll be showcasing in this video. So I'll be using Robin 2 with tac capital I, and this will tell us some things that we already know. We already know it's a 32-bit MIPS program. We can see the base address, so where the binary will start being loaded from. Okay. We see that there is no stack canary, and that's good because stack canaries are pretty pesky. If you're not familiar with those are, it's a special value placed after a buffer, but before the return address or before the program counter. And it's basically a checksum. So it detects. So the compiler will put it there, and before the program exits, it'll check the canary value. Because if you do a stack overflow attack, you're overflowing the buffer, the stack pointer, the canary, and the return address. And it will say, hey, this canary has changed. Someone must be doing something malicious. They must be up to no good. So I'm just going to exit. Typically, they exit with a stack smashing detected output message. So there's no canaries. That's great for us. And we can see here that the memory addresses are not being randomized, which is great for us. So there is no position independent code, which is great. So we want to analyze this a little bit further. Let's do lowercase I, and we can see some of the imported functions. So the C library or the embedded C library is going to be calling system and put string and printf. Okay, that's not super interesting. We do care about some of the exported functions. So let's do a QS, and I'm going to pipe this into grep tac v. And just to make it a little bit cleaner, we can see some of the other functions. We can see the main function right here. So this is the entry point of the program that we care about. I'm not sure why main's being listed a few times. And then here we see something called dat shell. That sounds pretty interesting. That might be something that we want to look at further. So this is probably the address that we want to change the program counter to. But let's actually open up this binary in Radare 2 so we can kind of analyze it a little bit further. If I do an IE, we can look at the entry point. If I do a I, capital I, it will give us the same output that we saw from earlier. I can do, let's see, FS to list different things. So we can see classes and imports and symbols and strings. So we didn't really look at the strings. Let's do FS strings. Because right now, this star, this asterisk, means all of these flags are selected. So if I hit F, it's just going to print out a bunch of information, which is fine. This binary is not huge, but if I just want to look at a certain thing, I'm going to do FS strings. Now I do FS, we see that only strings are selected. So if I do an F, it will print out the different strings that this binary is using. So we see the usage information that we saw earlier. We see welcome, okay. And then we see this congratulations message. And what's cool about using Radari 2 or something like that to look at strings instead of the built-in strings command in Linux is it will actually print the address and the offset of where it found this. So we saw before the address of the dat shell function. It was 00400950. And now we see the address of the string is kind of around there as well. So just interesting. What else can we look at? Let's do fs symbols and then run the F command. And we can just look at the symbols that are here. And we see that dat shell function again. And we can look around and we can see some other things. If I do seek to main, I spelled it wrong. So if I do an S, we can see our current address of where we are. If I do seek main, we see that has changed. We're now inside of the main function. If I do a PDF, cannot find function. Do I need to do PDF at main? PDF main. Did I analyze this yet? Let me do AA to actually analyze the function and now do a PDF. There we go. So now it actually prints out the disassembly. So this might look a little weird, it might look a little funky because it is MIPS and we're used to x64 on this channel, but we can see it does some things that we're kind of used to. If we know SP is a stack pointer, we see the stack pointer is being subtracted from. We're subtracting minus OXE8, so we're allocating space on the stack. RA is the return address, so it looks like we're saving the return address and we're saving the base pointer or the frame pointer. Okay, if we scroll down here, I'm really looking for these comments. I'm looking for calls to other functions. You can see a call to put string here, but if I scroll down, is there anything actually interesting here? Anything that we really care about? Inside of main, at least. You can see here, there's a basic check going on for 2 arguments. And if it's not exactly 2 arguments, it will jump down here and it will call put string, and then it will exit right here. It'll call put string if argc is less than 2, and then it exits. So this is the code checking for the usage. If I come back here and I type VV, it'll actually open up the main function inside of a nice graphical view, kind of like IDA Pro or what's it called? Binary Ninja. So this might be a little bit easier to read and look at. And I would encourage you to kind of step through it if you want, if you're very curious about MIPS assembly. It's not too important here. The thing that we really wanted was the address of that the dat shell function. So I'm gonna hit C to continue here, close out our program, and we want to replace this with the address of dat shell. And it's little endian, so we need to write this backwards. So 50, 09, and then 40. Come over here, rerun this, hit C to continue, and we still get a segmentation fault, but the address is different. The address is incorrect. So I was troubleshooting this for a long time, and I wasn't sure why it wasn't working. And there's actually 2 issues here. I guess maybe 3. I'm using Python 3, which no longer treats bytes and strings as the same value. So I need to add this B prefix right here. So both of these will be bytes. Come back here, rerun our target command, hit C to continue, and it kind of works. We can see some A's and then 50, but we're not really inside of our function. We can examine from the stack pointer. Okay, this is pretty funky. This isn't really where we want to be. So for whatever reason, doing this with Python was not giving me any success. So instead of doing Python, we want to actually do echo tac N for no new line and E to don't interpret these backslashes. So we know we want this address. And before this, we need 204 bytes of random data. So let's make this 204, and let's grab this, and let's slam it in here. And this looks very ugly, but this should work. So connect again, hit C to continue, and no, that's not the address that we want. So what's going on? So I was playing around with this for a while, and just like in some of our ROP Emporium videos, if we try to change the return address to the very beginning of the function that we want, it doesn't work. Something with the offsets, it just doesn't like. So let's see if we can seek to dat shell. Seek dat shell. Seek sim dot dat shell. There we go. VV. So right now we're trying to return to the very start of this function, and it's just not working. But I remember from doing ROP Emporium that sometimes you can go into an offset, like deeper into the function, and it should work. Something with the stack being misaligned. So let's come back here, and let's change this to 5C, which is an offset within that program, or within that vulnerable function. Connect in, hit C. Okay, we're getting closer. Let's actually wrap this. Does it want me to wrap this in quotes? I know this looks incredibly ugly. Control R, go back here. C to continue. Okay, so I had to play around with the syntax just a smidge, just a little bit. I know this is really ugly and kind of hard to read, so from the top, I'll just break it down. We're doing the change root command on the current directory to tell QEMU that we are making a new root directory or new root file system. So where we currently are, tech G1234. This is the port that the GDB server will listen on, and we'll connect into it in a second. This is just the vulnerable program we're running. And now here in quotes, we have 204 bytes of padding, or like random junk. So everything from this AA0 all the way to this AG7 are all just padding. It can be anything. It can be all A's. It can be whatever. It just needs to be 204 bytes of it. And this is the tricky part. We need to somehow get the address of the dat shell function, but not the beginning address, and offset into it. So we're just going to go a few bytes in. So offset 5C. So it should put us right here. So right when it's subtracting from the stack, and then it will just continue on execution from there. It should print out this string, congrats, I will now execute binsh, and then it should actually call the system call for binsh and everything like that, which takes place around here. Doing this in Python was giving us some issues. I don't know why. That might be something I have to look into further. So instead, we're going to use the echo command with tech E to don't evaluate these special characters. So this will convert to address in little endian. So it'll be 40095C, and this should work. So we hit enter. It's just hanging because it's waiting for our connection. So inside GDB, I will do my target, remote, localhost, 1234. Sweet. So it's successfully connected to our listener. We hit C to continue, and it just says continuing. No segmentation fault, no errors. So let's go back here, and we see it says, congratulations, I will now execute binsh. Perfect. I can do an ls. We'll see what directory we're in. I can do an ID. I don't have every Linux command. So if I do a who am I, that's not on the system, but we can look inside bin and we can do these different commands. So bin netstat antu, I guess, and we'll look at whatever netstat connections we have. Sweet. So I'm actually curious. Let me do a bin ps ef usage. Okay, bin ps, whatever. So cool. We successfully exploited that buffer overflow. Sorry that video took a little bit long. They always go longer than I expect, but I want them to be helpful. I want them to be informative. So I recommend, if you just want practice with MIPS assembly or just any type of IoT or firmware analysis, this is a great project. It's open source, and you can actually come here and look at the source code, intro stack buffer overflow 1, and you can compare what you saw in your disassembler with the actual source code. So we see here the buffer is of size 200 bytes. And then, so that's why it took 200 bytes plus 4 to overwrite the frame pointer. And then after the frame pointer comes the program counter or the return address, right? So we want to overwrite the return address. So that's why it took 204 bytes. We can see the usage information being printed out. And then we see the vulnerable function right here. It's calling stir copy. It's not doing any type of length check. Whatever we pass into that argv1 is getting passed to this buffer. And it's saying here, it returns OX41, just so you can see what register is being populated. And then here is the actual dat shell source code. Awesome. So that's really it for this video. I'll probably continue on and knock out some of these other challenges. I think next it makes sense to do this heap-based overflow. I don't want to peek and look at the source code though, and I'll save that for another video for another day. So that's really it, guys. Hopefully this was helpful. Hopefully this was beneficial. Router and firmware analysis is a pretty cool area of security research, and I want to showcase a little bit more of that on this channel. So please, if you enjoy it, like, comment, subscribe. And as always, guys, take it easy, and I'll see you in the next video.